Yes? Yeah, it was a very limited number of problems, right? I'll verify just to be precise here. It was it 9, right? What did I say? It's on video, I know that. Did anyone write it down? At a 4.5? 9, 11, 12, and 25. 25 is a really interesting problem. It's on the harder end of things, but it's something I've asked you to do. So, all right. If you enjoy these problems and want a challenge, try some of the others because they're all so different, you know. They're very, very different problems. Just for fun, you know, this summer. All right, here we go. We're moving on. In terms of our notes, we are wrapping up optimization. So just to kind of recap, 4.1 was the closed interval method. 4.2, we took a little detour, and I talked about the mean value theorem, and then we came back on, started talking about the open interval method and how we can basically use the open interval method to figure out the shape of a graph, where things go up, concave down. Curve sketching, real briefly, we talked about it, said I'm not going to ask you to sketch curves, you're welcome. And then optimization, we've just touched on that, right? Done a couple of examples. Newton's method is an optional section. We don't have to cover this. I like to when I have time. Unfortunately, we don't. For those of you who are computer science majors. So what this section is, it's basically Isaac Newton came up with an algorithm for finding the x-intercepts of a function using the derivative. And so the algorithm is what computer science majors use, or when you go solve an equation on a computer, they're using some form of Newton's method. It's probably been adapted, but it's some form of this method. So it's a really cool thing to show, but it's not necessary, all right? And then now we're going to do 4.7, antiderivatives. So if you look at what Cal 1, right, Calculus 1 is called differential calculus, the entire idea in Cal 1 is that we're taking derivatives or somehow applying the idea of a derivative, right? That's differentiation, so we call it differential calculus. There's a transition now into Cal 2, and that's where we are right now. We are going to start to be at a point where we are going to transition into the Calculus 2, and what we're going to be talking about is antiderivatives. So Cal 2 is referred to as integral calculus. Integral, we haven't even talked about what that word means, but it's basically the opposite of a derivative. So differentiation, differential calculus is Cal 1. Integral calculus or antiderivatives is Cal 2. All right? So let's start this with an idea here. Now, I have a Cal 2 student right now who's about to possibly fail Cal 2. And they were an A student in Cal 1. Okay, they came out in my Cal 1, they had an A. They took Cal 2, they're on the borderline of passing right now. And part of the problem with this particular student is that they were an A student in Cal 1. So they were complacent. They thought I don't really have to study. I just show up. I just watch them do problems. I'm good. Cal 2 doesn't work that way, all right? Even if you're good, I have yet to meet somebody who takes Cal 2 who can just sit there and watch me and then be fine, all right? So you're about to see why. Your ability to do Cal 2 is directly related to your comfort level with the differentiation in Cal 1. So the better you are at taking derivatives, the easier the Cal 2 is going to be. Not that it'll ever be easy, but it'll be easier. If you can't differentiate, Cal 2 is going to be an impossible roadblock for you. You'll just take it 2-3 times, quit, and change your major. That's what happens, all right? So you've got to make sure you're good with the differentiation. I'm not trying to scare you, just trying to be honest with you, all right? So here's a very fundamental problem, all right? Just a very simple problem. What if I tell you this? What if I tell you that the derivative of some function is 2x? Can you tell me what the function was? What?
It's going to be x squared.
X squared, right? So by looking at that, we should recognize that that's the derivative of x squared. So I know from this, so I say if this is true, then I can say that f of x had to be x squared, right? Because the derivative of that is that. Yeah? That's Cal 2. Wrap it up. Okay, is that the only answer? Can someone give me another answer that would work as well?
X squared plus any constant.
Okay, so how about x squared plus 3? Would that work? Yeah, because if I take derivative of that, the derivative of the 3 goes away, doesn't it? And so you'd still get that, wouldn't you? And I could have done, f of x equals x squared minus 5, right? Basically, any number I want added or subtracted to that, right, would work. So as a general answer here, right, as a general answer, my f of x would have to be x squared plus c. Now that c is any constant. And when I say any, I mean it could be negative as well, right? So just the fact that I'm using a plus is irrelevant because the c could be negative 2. And then that would be x squared minus 2, all right? This would be our general answer to that, wouldn't it? So that is the basic idea of what antiderivatives is can I give you a function and you go backwards to where it came from, all right? So let's try another one. Or let me do this before we move on. I want to change my notation because this is not the notation that we use in Cal 2. What we do instead is this. I'm going to propose the same exact problem. Exactly the same problem. But I'm going to say, let's say you have a function f of x and it's 2x. That is the derivative of x squared plus some constant, right? So what we want to do is, since I'm not using, notice I'm not using the prime here. I'm not saying the derivative of some function is this. What I'm going to do is I'm going to write capital F of x is x squared plus some constant. So the capital F tells you that that is the antiderivative of this. In other words, when I take the derivative of the capital F, I get the little f, right? That's the idea here. If I ask you to take the derivative of the capital F, you get that, right? So I'd like to give you another function. Ready? Let's do, so I'm going to give you a little f, and I want you to give me capital F, which would be what we call its antiderivative. I'll put all the notes up here and the language. I'll do all that in a minute. Let's just make sure we understand the idea. How about this one? 4x cubed. Raise your hand if you want to answer. Antiderivative, please. Somebody?
X to the fourth plus c.
Raise your hand.
My bad.
That's all right. I just want to give everyone opportunity. What do you say?
X to the fourth plus c.
Plus c. What do y'all think? Take derivative of that, you get 4x cubed, right? We have to have the plus c there because that covers all possibilities, doesn't it? Okay? Another one. Aren't we going to have a plus c every time? Like on every antiderivative we ever have. I'll just put it there now for you. Okay, who wants that one? Go ahead. Square root of x. How do you know that? Because you know, right? Because you took Cal 1 and you understand the derivative of the square root of x is 1 over 2 root x, right? So the antiderivative of this is this, right? Questions there? All right, let's do another one. How about this one? Who wants that one? This one's a little tricky. What do you take the derivative of to get this? Any takers? Let me ask this. Does anybody know what the power on the x here has to be? when you take derivative, you have to get an 8, right? So it has to be 9. Do y'all agree? If I take derivative of this, the 9 comes out, then I subtract 1, I get that, right? But there's a problem. The 9 comes out. I don't have a 9 there, do I? So how do I resolve that? I just put a 1 over 9 in front. See, if I put a 1 over 9 in front, what happens when that 9 comes out? It gets killed off by this, right? And now you just have the x to the 8th. See how I did that? Questions?
Can you repeat that one more time?
Yes. So remember the derivative in Cal 1, right? We're in Cal 1 still, but in Cal 1, the derivative of something to a power, the power comes out and you subtract 1, right? So if I have x to the 8th here, I know that where it came from had to be x to the 9th because I know that that power goes down by 1 to get this, right? But when I do the power rule, this is going to come out. If that wasn't there, I would have a 9x to the 8th, right? I don't want 9x to the 8th. I want a 1x to the 8th. So to resolve that, the 9 that comes out, I need to kill it off. So I put a 1/9 in front to kill the 9 off when it comes out in front. Kill it off and turn it into a 1. Yes? Everyone got that? Okay, how about this one? Ooh. Don't say 1 over 2 root x. That's the derivative. That's not what I'm asking for. I'm asking for what you take the derivative of to get that, right? This one's harder, okay? I'm not expecting that you're going to look at that and know the answer. So let's think about this for a moment. Do you all agree that this up here is x to the half power? Yes? X to the half? Okay, let's try and do it the same way we did this one. This was the function. Its antiderivative would have to be 1 more than that, right? So if that's 8, I added 1 to get 9. So what power, let me give myself some room here. What power would I need to have on that x in order to get it to go to 1/2? 3/2, right? 3 over 2. So if you add 1 to that, 1/2 plus 1, that's 1/2 plus 2 over 2, that's 3/2, right? So I need a 3/2 power here. That's not quite going to do it though, right? Because if I put a 3/2 here, yes, when I bring that down and subtract 1, I will get a half, but I bring that down and it's a 3/2 in front. I don't want 3/2 in front. What do I want? A 1, right? So how do you kill off a 3/2? 2/3, right? Hit the 3/2 with a 2/3 with its reciprocal. So you put a 2/3 out here. And that will kill off the 3/2. When I say kill off, y'all understand I mean turn it into a 1? So y'all see it? 3/2 comes out, boom, that becomes a 1. Take that, subtract 1, you get this. Y'all getting this? Yes? Okay, how about this one? How about 1 over x to the 3rd? All right. So I want to put something up here. It's going to be in red, which means you probably shouldn't copy this down. I want to put something, I want to ask you what this student did and whether or not it's right. What do you think? Can you tell what I did? I found the antiderivative of 1 first. So I said, what do I take derivative of to get 1? X, right? So I put that on top. And then on the bottom, I said, well, okay, what do I take derivative of to get that? And I played that same game that we were playing here, right? It was 3rd power, so I added 1, and then I needed to kill off that 4, so I put a 1/4. Do y'all understand what I did? Do you think it's right? It's not right, because what I did was basically, okay, so look, if I asked you to take derivative of this, right? If I asked you to take derivative of that, what would you have to use? Quotient rule, right? So when you do antiderivatives, it's the same thing. You can't do a quotient, you can't do the antiderivative of each one separately. You cannot do that. Just like in Cal 1, you can't take the derivative of a quotient by doing top and bottom separately. So this is not okay, all right? So what we have to do instead is look at this as x to what power? Negative 3. Okay, let's follow the same format we had here, right? When we're going from here to here, what are we doing to the power? We're adding 1, right? We're adding 1. So what would happen if I add 1 to this power? Add 1. I get x to what power? Negative 2, right? Negative 3 plus 1 is negative 2. Now, I still need my plus c. I don't want to forget that. And then what do I need in front? Because when this comes down, right, I want it to go away, and I want a 1 in there. So what do I have to put out there? Minus 1 over 2, not 3, because this negative 2 comes out first before you subtract the 1. Why did I make it negative? Because the negative times the negative would give you positive, right? And then these should turn into a 1. Are y'all kind of getting this? Yes? Right now, we are focusing our attention in a very narrow tunnel, what? Window, thank you. Very narrow window. We are only looking at powers of x right now. I'm not throwing some arbitrary things up here. I'm being very careful to only give you powers of x to find antiderivatives of. So I think we're ready. I think we all understand, I hope we all understand, the basic premise here is that we need to add 1 to the power, right? And then we need to put something out front that kills that off when it comes down. So let's try and find a general formula. Let's see if we can. Formula, question mark, maybe we can come up with one. If I give you f of x is x to some power n, we all already know in Cal 1 how to take the derivative of that, right? Derivative, power comes down, subtract 1. That's Cal 1, that's the power rule. But I'm trying to see, is there a rule, a similar rule for antiderivatives that allows you to go backwards, right? So let's see. The capital F of x should be, I'm going to leave some space in front, x. Okay, tell me about the power on that x. It's got to be that n plus 1, right? It's got to be whatever that n is up here, I've got to add 1 to it, right? I also have to have a plus c out here. But there's an issue, right? The issue is that if I take the derivative of this, this power comes out, doesn't it? And I don't want it there. I want that to go away, right? So how do I make n plus 1 go away? What do I need out front? 1 over n plus 1, exactly. 1 over n plus 1. Think about it. If I ask you to take derivative of this, the first thing you would do is pop the n plus 1 out, right? It would come out here, it would cancel out and become a 1, right? And then you would subtract 1 from that power, and that would be your x to the n. That looks like a formula, doesn't it? This is actually a formula that we're going to have. I'm going to formally write it down in just a second in a different manner. Any questions on this formula? All right, so if you believe that that formula is good, then I ask you to consider this. What happens in that case? Is that x to a power?
Yes.
What power? You could rewrite this as x to what power? X to the what? Negative 1, right? All right, what happens if we do x is negative 1? Do you see what happens right here? What's negative 1 plus 1? 0. What's 1 divided by 0? Undefined. Your formula just broke down, didn't it? The formula does not work for that. That's bad, right? But I have good news. That's the only one it doesn't work for. Because the only way this would ever be 0 down here is if n was negative 1, right? So that's the only case where the formula breaks down. But don't you know what the antiderivative of this is? Do you recognize that as being the derivative of something that you learned? What? Natural log. See, if you take the derivative of the natural log, what do you get? 1 over x. And so this is kind of a special case. If the n we have is negative 1, so if n is equal to negative 1, then we have this scenario, don't we? This is if n is not -1. This will work every other time. So in our notes, I have this written in a different form somewhere. No, I thought I did. I don't? Not there. Okay, that's all right. So let me write it down here. I'm going to give you the final form of this. This is called the power rule for antiderivatives. Antiderivatives. Do not confuse. This is not the power rule from Cal 1 that we started this class with a long time ago. I don't know if y'all remember how when I did that back earlier in this class when I showed you that the derivative of x to the n is n x to the n minus 1. When I did that formula, when I presented to you, I actually proved this using the limit, Pascal's triangle, and all this other stuff. So this is the power rule for derivatives. Now I'm talking about the power rule for antiderivatives. So if f of x equals x to the n, then capital F of x equals, now I'm going to put something here, it's going to look strange, but it's what we call a piecewise function. It's two different things. It's just 1 over n plus 1 times x to the n plus 1 if the n we're plugging in is not equal to -1, and natural log of the absolute value of x plus c if n does equal -1. Now, a couple of things. This is just saying what I just said. There's two different scenarios, right? There's a scenario when the n is not -1, and we just use that rule we came up with. Now, if the n is a -1, then it's the natural log. Notice I put the absolute value around this. That has to do with the fact that the natural log is not defined for negative numbers. So we put the absolute value to avoid that scenario. Any questions? Okay. Let's keep going. Let me show you the notes here, just so you see it. Look at that top one right there. A function capital F is called an antiderivative of little f on the interval I if the derivative of capital F is equal to little f. That's basically what we've been doing, right? We've been trying to find this capital F such that when you take its derivative, you get back that little f. Then, if capital F is an antiderivative of little f, then capital F plus c is the most general antiderivative of little f. Here, c is any constant, all right? So that's basically everything I've said, but just written down in the notes. So I want us to go back to this example that we did. Right, this is the one we started with, 2x, right? That was the one I started with. And I said, hey, what's its antiderivative? And we said it's x squared plus any constant, right? I'd like for you to take a look at this antiderivative. I'm going to graph it for you. We all know what x squared looks like, right? So this is what you see here in red is 2x, and the blue is x squared, right? And I'm going to move my constant. Right now it's x squared plus 0, right? If I move that up, plus a number, or minus a number, all it does is moves that parabola up and down, right? But no matter where it's placed, if I were to take the slope of the tangent line, go somewhere, here, go here. Do you agree that the slope of that tangent line does not change if I move it up or down, right? If I move it up a little bit, then at that same x value, right there, I have the same slope, don't I? So that's why the constant is like the constant doing the plus c, you have to have it because what it does is it creates a general answer. It's like a family of functions, right? This 2x, the antiderivative is actually a family of functions. Well, how many of them are there? How many functions are there that are antiderivatives of that? How many functions are there that are antiderivatives of this? Infinite, right? It's x squared plus any constant. It doesn't even have to be a whole number. So you have an infinite number, right? This infinite number of parabolas, x squared plus c, that have all been moved up or down. They all have the same property, right? They all have the same property. Where's my derivative? I thought I had a little slider here. Oh, there it is. See, they all have the same property that if you go to any x value, you see that? Go to any x value you want, the slope of the tangent line is the same at that x value for all of them, right? So the derivative of this function, this one, the derivative of all those functions at that point is the same. All right, let's do some more finding antiderivatives. Would y'all like a sneak peek at an antiderivative to find in Cal 2? You want a sneak peek at a harder one? You won't be able to do it, but just to give you an idea. This is a hard one. There. That's really hard. What do you take the derivative of to get that? So there's no more, like all your rules go away. You know, in Cal 1 we have rules, right? We have the power rule. What comes after power rule? Product and quotient, and then composition, so chain, right? That's it in Cal 1. Power rule, product rule, quotient rule, chain rule, that's it. In Cal 2, you have the power rule to go backwards, and that's it. There's no more rules that always work. So like in Cal 1, I think if you understand power rule, product rule, quotient rule, and chain rule, then it becomes very mechanical, right? Like if you understand product rules like derivative of the first one times the second plus the derivative of the second times first, quotient rule, derivative, right? There's like a formula for it. In Cal 2, there's not formulas, there's techniques, there's things you try. If you see this, you try this. And if it doesn't work, you try something else. And so there's not a clear path like the product and quotient rules create a clear path for you. So that's the challenge. So this one right here, we can do. All right, that just gives you a glimpse. Let's do something we can do. How about this? How about, all right, let me ask you something. When you take derivatives and you have constants that are in front of a function, the constant comes for the ride, doesn't it? How do you think it works with antiderivatives? If you have a constant in front, do you think it comes for the ride backwards? What do you think? What's your intuition say? Yes? Let's see if it does. Let's see if it does. I think we can convince ourselves. Let's go with this. Capital F of x equals something plus c, right? Let's ignore the 5 for now and just bring it here. And I don't know if this works, right? Well, you don't know if it works, right? It might not. I'm going to bring the 5 with me. There. Okay. Now, forget the 5. What's the antiderivative of x squared? 1/3 x cubed, right? 1/3 x cubed, using the power rule that we just learned, right? So let's put a 1/3 x cubed next to this. That's really 5/3 x cubed plus c. And the question is, did that work? Did bringing the 5 with us and just kind of ignoring it and bringing it for the ride backwards, did it work? Yeah, because if I bring this 3 out, what happens? Cancels out, and you get the 5 still, right? And then x squared. It works, right? So with antiderivatives, constants that are in front that are attached, they come for the ride as well, all right? That's good news, right? You don't have to worry about it. Same thing happened when you take derivatives. Any questions on how I got that? Did I do that too fast? Antiderivative x squared is 1/3 x cubed. We're okay? You have the power rule that you just wrote down, right? What's the power here? What's the power? 2, right? So you add 1, and add 1, and then in front you put 1 over that same number. All right, let's do this one. The antiderivative of 5. Well, that's different, right? Because remember, when you take the derivative of a constant, what is it? Derivative of a constant, you get 0, right? You only bring the constant along for the ride if it was attached to a function, right? Same idea here. That 5 is by itself. What is the antiderivative? What do you take the derivative of to get that? 5x. Right? 5x. Plus some constant. So all that happened there when you did the antiderivative of a constant by itself is that an x appears next to it, right? The derivative of 5x is 5. Ooh. Okay. Now what I've done is I've given you 2 terms, right? This is the first time we've had this. 2 terms. When you take derivatives, if you have addition and subtraction, can you do the derivatives individually? Yes? What do you think? You think we can do the antiderivatives individually? Yes, we can. See, this is more good news, right? It doesn't get bad until there's products and quotients. That's when things hit the fan, all right? So with an antiderivative, we are allowed to take the antiderivative of each one of these. So what's the antiderivative of this? We just did that, right? 5/3 x cubed plus, what's the antiderivative of 5? 5x, we just did that over here. And then we have to have a plus c. Always a plus c. Some Cal 2 professors will count the problem and count the entire problem wrong if you don't put plus c. All right? I'm not like that in the beginning. In the beginning, I'm kind of lenient about it, but as the semester goes on, you have to remember to put plus c. All right? Because your antiderivative is a family of functions, right? This is an infinite number of answers, but they all look the same. They all have the same like format. Questions there? Okay, how about this? 7x to the 4th minus 3 square root of